lot more frequently than you would think, only because, as I said, when you have a real beam, the beam has weight, therefore you have a rectangular load automatically with nothing on it. And then the triangular load happens typically when you have something that's like a dam where it's getting deeper and deeper and deeper in the water, or a retaining wall that's going deeper and deeper in the dirt, because there's more and more force as you go down. And so it starts at the top with very little water pressure load, but then as you go down, it gets bigger and bigger. So retaining walls will add that to it. But that's not super common. It's common enough that you're going to see it, a number of times in a year, but not like once in a lifetime. So let's see. So the main thing is this: when I put moment on a rectangular beam like this, I'm going to have compression on the top, and I'm going to have tension on the bottom. And make sure you understand that literally means it's getting shorter and longer. And then this, in the case of a rectangular beam, that's going to be perfectly in the center, that neutral axis. So this gets shorter, this gets longer, and this has actually no change at all in its length when a moment is applied to it. And so to skip kind of ahead a little bit, and maybe I'll decide how much I'm going to go back and backfill this. I spent all the time to totally build these formulas, and it's really cool, but I'm afraid it's going to take a half an hour and we have so little time left. Main formula is this: sigma max. Again, do you see why we're asking for sigma? Stress. PSI, pounds per square inch. How much stress is on those top fibers trying to get smaller, shorter, and those bottom fibers trying to get longer? It's found by multiplying the moment. Of course, that makes sense, right? What does it determine on? Well, how much moment did you put on? How much did it want to bend? If it doesn't want to bend much, it's not going to have much stress on it. If you want to bend it a lot, it's going to have a lot of stress. Multiplied by C divided by I. C is this distance right here. Just like it was in the case of a shaft. It's like, how far is it from the center of the shaft to the outside edge of the circular shaft? It was like the maximum distance. So a similar formula to this is not max, but just sigma, and that's my over I. And that's where if you say, well, I'd like to know the stress at some random location, like right here. If you said, oh, okay, I want to know it right there, and that distance is y, then it's just some shorter distance. And that c, by the way, is both directions. In other words, how far is it out to the kind of the bottom end? In a beam, again, that neutral axis is really easy to locate, because if your beam is 12 inches tall, it's in the middle, it's 6. If it's 40 inches tall, it's in the middle, it's 20. But we're going to look at some shapes later in this class where that isn't the case. The I-beam is another kind of a classic shape, and this is very commonly what we use in our culture to structurally make something stand up. And even that has a super simple neutral axis because it's symmetrical. It's not a beam, but since the top is often the same exact size as the bottom, then that neutral axis right there, I better write NA up here. That neutral axis right there, you don't have to do any calculation for it. So that distance C would just be the distance, up to the top. But we're going to look at a problem sometime, maybe like this, where now all of a sudden the neutral axis is really hard to locate. You understand that? And this is not an uncommon shape. Does it make sense this shape would be, well, a place where you were very worried about compression? Because there's a lot of material up there to keep it from compressing. And of course, that's going to keep it from bending. If there's not much material up there, then it's going to want to bend a lot. Maybe I don't want it to bend. Okay, that's a roadway. There's trucks driving across it, trains. And so, okay, let's put that up there on the top. Maybe down in the bottom in the real world, you'd put like some thick cable that ran all the way through this in the bottom, and that cable is not going to want to stretch if it's really thick, like the Golden Gate Bridge. And so maybe I'll just put a cable in the bottom side of that, and that'll take care of the tension in the bottom. So there's these things called post-tension beams, where they pour concrete beams like this, and they put a sleeve of PVC through it, and then they run a cable through it with threads on the end, and they tighten it up, and it literally takes the I-beam, like for a bridge out there, and they'll tighten it so it'll actually lift it up in the air and put camber to it, which is what they do for all, even like trailer loads for trucks. If you see them empty going down the road, a flatbed, you'll notice they're not flat. They like curve like this. That's because you're going to put weight on it. And wouldn't it be cool if it went to flat so then it behaved normally, instead of, you put it on flat and then it's like, sagging down to the road, so to speak. So they pre-tension it to have camber to it, expecting that the load will then flatten it out and it'll be easier for forklifts and it'll drive better and so forth. So you can actually take these concrete beams and put them out there and then crank the tension up on that bottom, and that'll keep it from wanting to bend as much. And you can even pre-crank it so that it lifts up in the air, which is unbelievable. If you make that shorter, it has to lift up in the air. It's just interesting. But see, the problem is, does it make sense the neutral axis in this example is going to be pulled way up higher, thanks to the fact that there's a bunch of material on the top? And with respect to neutral axis, what we're really talking about is just where's the area match up. In other words, you got area on the top, you got area on the bottom, and then that area matches up is kind of the gist of it. It's a little more complicated than that, but that's kind of the gist of it. And so we got to calculate this neutral axis, but it isn't always going to be so simple. So does it make sense in this problem? There's kind of like C1, C2. I can't just say they're both C now, because they're not going to be equal. So down here in a normal load, this is going to be the tension, this is going to be the compression. Right, COMP and TEN, since I already used C for something else. So these two formulas that I highlighted back here are some of the most profound formulas that exist, and collectively they are called, or they're called the flexure formula. In other words, how much flex? You got to know how something's going to bend, right? You can't just put weight on and go, ooh, how good it didn't break, because it might bend too much. Incidentally, and I mentioned this before, but this works sideways too. In other words, if you have a building that's vertical, that's a beam too. And now I got wind blowing on it. Does it make sense? Because it's attached to the ground, it's going to want to do this in the wind, kind of lay over sideways while it's bending too. That's like a beam, cantilevered beam coming out of the earth. It doesn't always have to be horizontal to be a beam. And if that bends too much in the wind, like the people at the top level blow chunks, and I mentioned in one of our classes that they even have a whole system in the top story of those to counteract that. Because you can't just build a building out of solid concrete, and because it costs too much. So we want it light, but if it's light, then the wind's going to want to blow it around a lot. And so this business of something bending, flexing, that's why this formula is so stinking profound. And so the things we got to get good at now, for the most part in these problems, we're going to just be told, oh, there's a certain amount of moment on it, but does it make sense in a big picture? What would be really cool is to take like the problems that you just did that have a bunch of loading on them and find the max. Like you'd have to literally draw a shear moment diagram, and you have to do this in a few of your questions. Literally draw a shear moment diagram to determine the maximum moment, and now you have M. Now you have M for this formula right here. And then C is that distance to the neutral axis. And then I is second moment of inertia, which we've got to learn to calculate now. That's what we're calculating. And then I can multiply all that stuff and wonderful things happen. Let's take a quick look at the note sheet for this, just so you're. So we skipped a bunch of this thanks to running out of time. Thought my notes were more complete than this, but actually I have an updated note sheet. This isn't even all of it. Does anybody have theirs? This is what you have right now, right?
Yeah.
So I've got some other stuff on here, and I'll give that to you because there's some other formulas pertaining to I that you don't know. So I guess what I won't do, which is kills me based on my temperament, is I will not show you where these formulas come from. Let's just see if we can go use them for something. So what do we got? Let's do an example. That didn't work. Oh, you're an idiot. I did it again.
Do you want the sheet?
I need to be able to draw on it, so let's take a second.
You know, we want to say, let's go with some stuff. Like, sick. Well, sounds good, yeah.
Well, I guess while I'm here, I can pull up the correct note sheet too, so.
We gotta go over safety.
What's that?
We gotta go over chainsaw safety.
No, we're just gonna start using the chainsaw. We're good.
No shot we cut ourselves, right?
I don't, what could go wrong?
He just threw it in the chaps. It's like, yes.
That's one of my favorite lines. What could go wrong?
Like that guy that his law is like whatever came wrong with that. Or is that working well? No.
God, you're right.
No.
No, you're right.
No. Dude.
My favorite is use the same ones that you.
Oh, man, you're right. You were right. I just think
Get these.
your name Murphy's fast sign.
I want one like you.
Yes.
And then you have got an often.
What's up? So really?
Like the simplest solution is the solution. Something like that.
Oh man, I follow that rule to a T. Occam's.
Occam's razor.
I can follow this a long time. Whenever I like don't know, I'm like everything chicken skin to it. I'm like, it's probably the simple, right? Like,
Let's see, do I have this note sheet that I can pull up super quick that I can steal as well?
You guys teach me how well. Ask them, where's your welding mask? Put your squints on.
you put your squint on though. That's awful.
I think he was really talented at what he did.
Good catch. You should- it's a bit of it. Sorry, I had my squints on for a second.
Okay, so here's the stuff that is added. We're back in the game now. Sorry about that. Yeah, so in the interest of time, we're not going to have a chance to look at this super deeply. So we got these two basic equations. Awesome. And then how to find the moment of inertia. Now we did this as a part of a project. You remember that at least vaguely. 1/12 BH cubed. We said that if this is the base of it and this is the height of it, when a beam is installed vertically like that, that's what I do to get the I value for it. The moment of inertia, I, huge number. And you saw the other day in the BCI guide that, you know, those numbers were listed in there. We know how to calculate those ourselves. Notice though, for one that's built up, a built up collection of rectangular beams, this gets a little more complicated. So we'll take a look at that in just a minute. But to start with, to keep this nice and simple, let's tackle this first example and we'll pop back and forth as necessary to that note sheet. So notice that's what you saw at Boise Cascade. It's a built up I-beam, but notice, like I said before, it's very symmetrical. Notice the top of that and the bottom. The top flange and the bottom flange are 6 by 1.5, and then the middle is 12 inches. You can probably appreciate that, you know, sticking a few nails up here is not going to do it. Like you got to screw, you got to glue, and that's really got to be connected well for this to work. But does it make sense that the neutral axis in this case, I don't have to do a bunch of calculations to calculate it, and it's going to be awful in a minute to calculate that, but does it make sense that that neutral axis right there is right through the center of that thing? So that'd be 6 inches up, and I just know right where it is then. That's kind of cool. So we want to determine the maximum bending stress. That's code for that formula I just showed you a minute ago, which is the moment. I need that, I need the distance, and I need this I value. Those are my ingredients. And because this is not just a rectangular beam, and you might want to write this formula down just since you don't have it in front of you, but because this is not just a rectangular beam, notice it's a built up collection of rectangular beams. The I value is a little more complicated to calculate. So let's use this formula and see if we can calculate it. This expression right here is what is referenced right there. Unfortunately, like I here is, this is the equation for I for a rectangular beam, but I is different for a built up beam, but it's based on that same exact formula. And so down here, they called it I bar. And I probably would have made my own lingo up for this if I felt like I had the freedom to, but you know, in your book, you might read it. So I still do the 1/12 BH cubed thing to it, but then I add a bunch of junk to it kind of after the fact. And so, and notice it really comes down to, so this is the form, these two formulas are what I want you to write down. Actually, you don't need to, I'll just take a picture of them. Bring them over.
Glad you put the center much more on. I was like, I know we like to do this, but all the stacks. Center mass.
Oops, I don't want to copy that. I want to crop it. So let's just take this down a little bit. Moment of inertia. Okay, so we know where the neutral axis is. Cool, that's great. We were told it's 1 kip foot. So does it make sense? They're just telling us that M is 1,000 pound-feet or feet-pounds. That's our moment. So that's kind of cool, right? Because I can just plug it in. And because that neutral axis is in the center, I want you to stare at the figure. Can you tell me what C is here? So it's the distance all the way to the top. So it's 6 basically in that web, and then 1.5 inches more. So does it make sense? C is 7.5 inches. And so it's like, God, this is working great. Like, this is awesome. I know M, I know what C is. Notice I got a unit problem there because one is in foot-pounds and the other one's in inches. So maybe, you know, do I care? Do I have to convert inches to feet, or do I have to convert feet to inches? I might have to think about that, right? Because remember, sigma is going to come out in this case. It needs to come out in PSI, pounds per square inch. So that makes me think I should turn the pounds to inches, you know, so I'm thinking about that. But what about this I value? What's the I value of that beam? Again, it'd be nice just to look this up in a table somewhere, right? But this is where the table the table comes from.
So is it the I value of all three rectangles for I bar?
That's exactly right. So I basically have three rectangles down there. So I'm really looking at this formula right here. But I realize that the I that this is referencing right here is that. In other words, that's how I get it. So, okay, well, let's look at the kind of the top and the bottom. Let's calculate what I is. So according to that formula, I get regular I. So if I look at the top and notice the way it's oriented, it's really important to understand that this is B and this is H. So notice that top piece up there, it's actually laying sideways, isn't it? So that's not good. Like that's not a good way to lay this in terms of its I value, but notice its width is 6 inches. So it's 1/12 times 6 inches wide times 1.5 inches tall. The only thing that's missing is that's cubed, right? So that's the I value for that top number right there. Well, at least this portion of it. But the second part of this is not just how much material is it? So does it make sense to you? This is really important. That if I take this beam and I go like this on it, that top wants to get shorter. So it would be nice if there's a lot of material up there. But the second thing that's important is where is it? Because if this top piece right here is a lot higher in the air, then it has to get a lot shorter and it doesn't want to. Does it make sense? Something this small is going to want to bend really easy. That's because this material right here is only like a couple centimeters away from the top. And so it isn't hard to get that to bend. But if it's way up here, does it make sense? It has to get crushed way more. And if it's wood, it's going to say, I don't want to do that. It's not going to want to bend. You want stuff to be tall. So the second part of that formula, that AD squared, it's basically saying you got that area up there, right? And that area doesn't want to bend. Well, where is it? What's its D? How far away is it from the center? So thanks to that 12-inch web in the middle, it's pushed those two portions of that beam way away from the neutral axis, which is going to make this thing not want to bend now. Does that make sense conceptually? That's the top and the bottom that are doing all the work here, right? And so if you put that top way up there, it's not going to want to bend. Well, didn't we say the neutral axis didn't bend at all? Yeah, the stuff in the middle doesn't bend at all. What about the stuff that's barely above it? Still doesn't want to bend or change length much. Get way up there, now it wants to change a lot. So the second part of this formula, the plus AD squared part, is not just what is the kind of the I value of the material on its own, but where is it located? So what's the area of that? Oh, that's easy. That's the same numbers I just had a minute ago. That's 6 inches times 1.5 inches. That's the area. Now, where is it relative to the neutral axis? D is the distance from center to the neutral axis. And then the key to this is how far is it from here, the center of it. It's not how far is it from the top or how far is it from the bottom. You have to treat it, well, like a particle. In other words, that area, where is that area located? We have to define that by its center. So how far is it from there to here? That's D. Yeah, half of an inch and a half is 0.75, and then there's 6 more inches. So that's 6.75 inches. And what do I do to that number? Square it according to that formula. So the distance has a squared effect. That's why the distance is so powerful. It's saying the area is powerful, the distance is twice as powerful. The distance is the most important thing. And that's why you saw in those I-beams out of the factory, the inner part of that was like nothing. There was like hardly any structure to it all. And they said, oh yeah, you can punch holes in it. It's like, it doesn't even matter, because its purpose is just to keep the top and the bottom apart. As long as you haven't punched so many holes that the top and the bottom can move together, fine, because they're doing all the work. That distance out there, extremely important. Now, what's going to happen when I go do this for the bottom one? Isn't it because of the symmetry of this? Isn't it going to be the exact same answer to that? So instead of kind of redoing all of this, I can just say times 2. And I'm being a little lazy here, but notice all of these measurements are in inches. But take a look at the units of this. 6 inches, 1.5 inches cubed. What's inches times inches cubed? Yeah, inches to the fourth. And notice over here, this is inches times inches squared. Notice that's also inches to the fourth. And so the unit for I is inches to the fourth. It's just weird. I mean, again, we've seen that a little bit, but not formally. Okay, cool. Well, now we got the middle one, right? What's the middle one? Switch to blue since we can. Same calculation. Good job. But notice the D for this one is actually 0 because it's centered at the middle. So I'd say, okay, it's 1/12 times the width, which is 1 inch, times the height, which is 12 inches, and the 12 gets cubed. And then plus 1 times 12, but times 0 squared. And so that term goes away. And for that reason, when you're doing just a normal beam, when it's a beam and it's not, and that's why the note sheet said for a beam, just do this formula. For a rectangular beam where the whole thing is rectangular, the center of the neutral axis is right in the middle of it. Therefore, it won't have a D. And so they're basically just saying, oh, you just need the 1/12 BH cubed formula. And you won't remember this, but when we did the lab in class where I bent that beam and so forth, I showed you the calculus as to how to create that 1/12 BH cubed. In a sense, that project might have been better now, or after this.
There's no way that problem. It's good.
What's that?
It's a hard problem. I was gonna say, I was like,
Super hard,
we're not
yeah.
going to do that.
Yeah, it's not going to be, that's not going to be easy no matter what. So notice this is also inches to the fourth. And so if you punch all that in your calculator and you don't screw it up, you get 967.5. Do you agree that's our final ingredient to our recipe for sigma? Yeah, so let's go ahead and let's pay attention. And by the way, notice we're asking for maximum bending stress. That's why there's a C here, because we're putting in the maximum distance possible. If you say, what's the stress like 2 inches up, you can find the stress anywhere you want. But then you would just put a different value. How far away from the neutral axis are you? Is that where you'd like to go? What's going on right there? That's where, the guy was talking about people screwing stuff up. It's like somebody drilled a hole in it somewhere and they're like, okay, what's the stress right at that point right there? Okay, well, that's 2 inches up and we'll find the stress there and see if it can handle it. But it's like, we're done now. We say, cool, sigma max is equal to M, which we said is 1,000 foot-pounds or pound-feet. And I'm thinking we need inches. Therefore, don't we need inches on the top and feet on the bottom, which there's 12 inches in 1 foot. And so, okay, that puts that in inches. And then we multiply that by C, which is 7.5 inches. So would you agree our unit on the top is pounds square inches right now? Our unit on the bottom is 967.5 inches to the fourth. Are the units going to work out for us then? Yeah, because 2 of the inches on top cancel with 2 on the bottom, and now we have pounds per square inch, PSI. That's rad. So it was important that we switch that moment measurement into pound inches, so to speak. Pop that in there. You get 93 PSI approximately.
That was the maximum moment.
So that's the worst stress. We agree that the worst stress on this happens at the top and the bottom of the beam. And so we say, in this case, the top and the bottom were the same location. And so we said the worst is at the top and it's 93. Now we would look at a table and say, can that blue spruce material that we used handle 93 PSI, or is it going to go crush under that load or pull apart under that load? So we'd be able to pick material now. And if that material didn't work, we could change material. And if we couldn't change material, then we could change the dimensions of that design. We could say, let's make it taller, let's make it shorter, let's make it wider. It doesn't have to be 6 inches, let's make it 8 inches. Pick something else, pick a different size beam. So do you see how close we are to like being able to make stuff that we know is going to work? I mean, isn't that rad?
So like, in terms of like that height issue where they cut top, would we just reduce the, I guess, the base in our equation? Even though, like, putting aside that it's not symmetrical on each side, like.
Right.
theoretically simplified,
Yeah. That's exactly right. If a chunk was taken out of that, then we couldn't say it's 6 by 1.5 anymore. We'd have to say it's 4 by 1.5 or whatever, and see if it can still handle that. And if they're lucky and there's enough extra built into the whole thing, then maybe it'll be okay and still not fail.
That's kind of what they would do there. It'd be like, okay, worst case scenario at this point where it's going to be at its worst. Like,
Yeah. Yep. And then usually there's all kinds of cool stuff you can do. Like the only part of that beam that matters is the top, because that's where the floor is. So you can add all kinds of wood under the sides and below it and kind of beef it up. You can glue a whole bunch of stiffeners in kind of inside in this area. Does it make sense if I added another board kind of right through the middle of that? Running back here, like that could stiffen it up a little bit. That'll help. Or maybe I add some stuff here, add some chunks right there and glue it together and so forth and make that top web longer and run it for, distance like way down the board. So I can beef it up a little bit. So yeah, there's things you can do to fix it. But again, that's the kind of thing and where it was kind of cool that he was talking about, because that's where you guys could take what we're learning right here and literally walk out and make some calculations and then, go stamp it. And it's going to be okay. And then they're going to pay you $1,000 for that. So it's pretty rad. And there won't be one other person that can do it. Let me they asked for a 3-dimensional drawing here, which is terrible, but I want to show you this because it's kind of cool. So here's a side view of your, I'll draw this a little better. Here's a side view of your beam, and really they're lined up, but I'll draw the end as though it's like a hair back a little bit, just so you can kind of see. Can you see that's a side view of it? And then here's a little drawing lesson, but that's how you show. There's more stuff over on the left, but no one cares. Now, does it make sense that the top is being pushed on in compression like that, whereas the bottom is actually being pulled on? The top fibers are getting pushed on. That's why they're getting shorter. And of course, that would be happening on the other side as well, right? So the top is being pushed on, which is what's making it shorter, and the bottom is being pulled on, which is what's making it longer. Now, those are the maximum values. What's happening in the middle? Well, there's no pushing or pulling at all. That's why it doesn't change length. So in the end, if you kind of draw this rectangular right here, I'm sorry, this triangular load, this is an example of a place where it's causing triangular loading. So the maximum is right up here, and it's being loaded less and less as you move down, and therefore the middle fibers are not getting as short as the top fiber is. The top fiber is getting the shortest, and then they get progressively less until they go to 0. Over here, it's just doing the same thing, but going the other direction. So notice the arrows, those are going. This is compression, this is tension. That's what's happening in there. So you can see, if I say this is, I guess I have to write COMP. If this is C all the way to the top, that's maximum, but you could go any place you wanted in here, and that would be Y. You can put any distance in you want. We put in 7 3/4 because we wanted the maximum compression, because of course we do. We want to see what's going to break here. So we want the maximum, but you could go to any place you wanted to in this. So that loading should look familiar to you, because that's the loading we just put on stuff in the last section. That's kind of cool to see, I think. Okay. So here's what I want you to do. So pull out 653 now, because I got to go get that for us again. And what I want you to do is stare at that. And I'll pull it up right now so you can look at it just to make sure you found it. One. And it's interesting to me that this is in the book. I'm in a different location, but notice that beam's a little more complicated, because do you agree the neutral axis now, we don't really know where it is? And that turns out to be quite a calculation. So we got to make that. But I just asked the same question. I made my own problem up for this, but notice I said, hey, here's a beam. It's all measured in metric. And we're told it has 600 Newton meters of bending moment on it. And we just need to know, well, the same thing, except for this time I said maximum tensile and compressive stress, because in the last problem, they're going to be equal because the neutral axis was exactly in the middle of the shape. So if I'd went down or up, I'm going to get the same exact answer. Does that make sense? This one, however, the neutral axis, and they kind of have it drawn in there, is right here. It's kind of like higher than the middle. And so for that reason, the distance from here up to the top is smaller than the distance from here down to the bottom. And so we're not going to get the same answer for compression as we do for tension. And by the way, that's important because some materials don't work well in tension. Concrete does not like tension. It just pulls apart. It's not glued together very well. Awesome in compression. Put concrete at the top of your beam, if you will, but put a cable at the bottom. Cables are awesome in tension. They like tension. They're terrible in compression, right? Wobbly, they don't do anything. So we're going to get two different answers for this in this case. Now that looks like just a bunch of wood and they used all the same wood. And so in the end, we might be curious as to which one is the maximum of those two, but they're two different numbers here. And that's what's kind of cool. What I want you to do is see if you can calculate the I value for that. Like start playing with that while I quickly, and I'm going to catch up to you very quickly, but can you do the same thing that we just did? And the other thing I want to say is, yeah, no, you're okay. So start calculating the I value and then I'll be right with you in a second.
Yeah. This one is 1040 because of spec. Seven here. Good.
So the problem you run into very quickly is the D. Did you notice that? Because how far is it from the neutral axis? Well, if you don't know where the neutral axis is, then you can't know D. So you can get that, you can get the 1/12. So let's start on that maybe down here. So let's see, I'm trying to get I here, and I say, okay, cool. I'm looking at that little side piece down there, and it's like, and again, I'm kind of wondering, should I be switching this to meters? Should I be doing this in millimeters? I'm a little worried about that. I mean, what's your thoughts on that? Should I be switching?
Switch all the meters.
All right, let's do that. Let's see if that's a good decision. So that first, I'm looking at this rectangle right here. I can see it's 20 by 150. So its value then would be 1/12 times 20, which would be 0.02 meters, times 150 millimeters, which is 0.15 meters, except for that's cubed, right? So that's the 1/12. And so great. And then I say, okay, then that's added to its area, which is again 0.02 meters times 0.15 meters. But now all of a sudden I've got distance squared. And the problem is the distance is measured from the center of its center to that center of mass. In other words, that's my D right there, that neutral axis. But I don't know what that neutral axis is. Like we got to calculate that, right? So this is something that I showed you in calculus based on formulas and so forth, but now we got to calculate this. And so here's how you get it. Calculation for locating the neutral axis, center of mass. You basically find the areas, you add up all the different areas. Now in our case, we have 3 different areas, right? 2 of them are identical, but we have 3 rectangles to add up. But then you also add up that area multiplied by the distance. In other words, how far is it away from something? So, what does that mean? So just to make the notes look good, let's again snap a picture of that or turn it off. Smooth move, X-lax. Is that still a phrase? I don't think so.
I think about it every now and then. I don't say it.
I think about it every now and then. That was a classic.
Process something I might pick up one day again. But
Well, now you've heard it, so you can fire it up anytime you want to.
yes,
Yeah.
fix it, you should, but
So not quite so easy now. So we got to kind of like, we're gonna have to put that off till later because we don't know what's going on there. So let's get the center of mass then. Okay, fine. What does that say? That says if you take the distance, you take each shape, its area. Okay, I got that area. Same area you had before. So that'd be 0.2, 0.02.
so are we measuring from rim to rim?
Yeah, that's a great question. 0.02 times 0.15.
But they're horned rims, so
That's right.
we can't see what you're doing.
Oh, God. I didn't know what you're talking about.
You're like, they are horned rims.
Horned rim, that guy, what is he talking about? How to get back there. This is what happened the other day, and I don't know how to fix it. What I did last time was just keep pushing buttons until something beautiful happened. It's not end the meeting. That was useful. Let's try resharing the screen. Let's try resharing this screen. Got it. Share screen. Yeah, baby. So there's my area. But the question is, how far is it away? Well, away from what? Which is, the question is, the answer is, you can put it any place you want. So I guess I'll put it, let's see, I'm going to do it from the bottom this time. So see, I don't know where the neutral axis is. That's the problem. And so if I put it there, that doesn't really make any sense, but I can't put it where it is because I don't know where it is. You can actually put this anywhere, top or bottom. It doesn't really make any difference. So because I'm kind of calling this the datum, that's what my distance is going to be measured to. And so this is the distance I'm after here. What did that formula say? Y. So it's like, this is my Y, the center of this down to some location. So I'm going to measure them all from that bottom location. Doesn't matter where. You can pick anywhere. You can pick right there. You can pick right there. Those would be the three places that would make sense. You can go way down here if you're crazy. Doesn't matter. Okay, so how far is that away? Well, because again, it's measured from the kind of the center of mass of the shape. In other words, this is the center of that area right there. Then because this thing is 150 millimeters tall, then that Y distance would be 75 millimeters. You agree with that? That's how far it is away from that datum. So 0.075 meters. There's one of them. Now, like last time, would you agree when I jump over to this one over here, I'm going to get the same exact answer? Because it's the same exact shape. So I'm going to say times 2 of those. And now I got to move to the top. So based on what I just said, how far is the top away from that line? In other words, that Y value right there. Exactly right. It's the middle of the shape, which is 12.5 plus the 150 I already have. So was that 162.5? And its area. And what is its area? Notice I got to work a little bit for that area. I can see it's 25 tall, but they never told me the whole width of it. They told me it's 20 here and then another 200 in the middle and 20 more there. So that's a total of 240 all the way across the top. So it's 25 by 240. Now that's just the top of this. Now on the bottom, I've got to divide all of that by all just the areas. So I have 2 of those 0.02 times 0.15s, and I have 1 of these 0.025s by 0.24s. Agree with that? Now, out of curiosity or out of I'm looking over at my notes, and I did this in I did this in millimeters. So maybe I converted it later. Maybe I didn't need to convert it. I'm not really sure, but I'm going to go ahead and I guess punch this in because I don't see any other way. 0.075. And because I'm typing the whole thing in all at once with a bunch of plus signs, I got to be a little careful and put parentheses around the whole top section. I got 0.11875, which is correct. Same thing I got before. So Y bar is equal to 0.11875. I was kind of lazy with units, but can you tell me what those units would be based on what you see up there? Notice this is meters, meters, meters. So that's cubic meters on the top. And over here is the same thing, meters times meters times meters. That 2 is just the 2. So that's cubic meters on top. What is it on the bottom? Meter meters plus meter meters. So you have square meters on the bottom, cubic meters on the top. That would cancel to leave meters. Oh, of course it is, because that's a distance, right? So what did that just tell us? It just said, guess what? Your neutral axis is 0.11875 away from that axis you just chose. So that means this distance right here to that neutral axis, that is 0.11875 meters. So now I know where it is. I know where the neutral axis is now. Now, would you agree that looks about right, at least based on the way that they drew it? Notice that's really 118.75, and here it was 150, right? So it's a little below that, but it's not 75 because there's all that wood up top. Isn't that wood up top going to pull the center of mass up there quite a bit higher than it was? And again, think about what this means. It means if you put weight on that thing and it started bending, that line right there is the neutral axis. It won't get any longer or shorter. The top is going to get shorter, the bottom's going to get longer, but it's totally based off of that kind of arbitrary location. That's kind of cool. It's an amazing calculation. So in case we need it, I'm going to write 118.75 millimeters here, in case we decide we need to know that. Okay, so meanwhile, back at the wrench, what are we doing for I then?
That it's y bar minus.
Yeah, see, the key is how far is it from here to here? This is the distance we need. Because we know where the center of our little rectangle is. And we knew that that was 0.075, right? That's how far it was. But then the center of mass is actually 0.11875, so it makes sense. I need to subtract those. It's a pretty small distance. In other words, that rectangle is pretty closely located to the center of mass. So if I take 0.11875 minus 0.075, I get 0.04375.
We're measuring from the bottom up.
Yeah, so this is like the distance from the center of mass of our rectangle. Because remember, that's how it's defined. Like, where is that rectangle located? It's located based on its center to the neutral axis. And according to the formula sheet that I didn't bring over here, what's wrong? What's missing from that? It was area times distance, but the distance was squared. And there's two of those because the other one's identical. That's exactly right. So I can just say times 2. And now let's move on to that one up on top.
Down to our neutral axis or your center of mass.
Yeah, that original shape, that original red datum that I stuck there, if I had stuck it on top, then I would have got a totally different value than you, because then I would have got that distance right there, and I would have put it in the same location. But had you gone from the top, you would have got a different number, and we'll still get the same answer though. That's what's kind of cool. And since we're staring at this anyway, didn't we say the whole thing was 150 plus 25? It's 175 all the way from tip top to bottom. So if this much of that 175 is here, then couldn't I go 175 minus that to get that length up there, which I'm going to need in a second anyway. So if I take 0.175 minus 0.11875, I get 0.05625. So basically the maximum, that's kind of like the C value for compression. And this is like the C value for tension down there. Does that make sense? So now I know how far they are away from the neutral axis. I'll need that later. Okay, so let's keep adding. Let's add that top. So again, you start out with the 112 BH cubed number. And I'm going to start being lazy again and leaving out all the meters for this stuff. So the width of that thing we said was 240. So that's 0.24. That's the small one. And then the height of it is 0.025 because it's 25 millimeters. But remember, that's cubed. So there's the 1/12 BH cubed number. And then plus the area of that shape times distance again. So area 0.24 times distance 0.025. I'm sorry, area. And then times the distance, but the distance is not 0.0625. What's the distance? Yeah, it's like the center of that down, right? It's the center of that down. So if I took this number and subtracted 0.02, half of 0.025, which is 0.0125, if I took 0.0125 away from 0.05625 minus 0.0125, I get 0.04375, which coincidentally is the same number we just got a minute ago. And that's totally a coincidence, by the way. And that's squared. So there's my I value. That's the, and remember that, what does the I value tell you in simple language? I shouldn't say remember, because I don't think I've even taught you this yet, but in simple language, if I say, hey, this beam's got an I value of 97, what does that tell me about it? Its ability to resist shape changing. That's really what it's telling you. And it has to do with the shape of it, not the material. So this is just a rectangular beam, and so it'd have one I value. But if I took the same exact material and I stole the material off the sides here and put it up on top, that would now have a larger I value. So I-beams have a better I value for the amount of wood that you have. That's why those engineered I-beams are so cool. It doesn't do any good. Like if I just cut this part off, you can't glue it up on top. You're just throwing it away. You might as well not waste it. Just cut it out of a tree, boom, there's your beam. It doesn't cost that much money to manufacture that. Cut, I'm done. There it is. What they did out there, super complicated, but it's using the materials a little bit better. So what do I get for this I value? I get 0.00003453 meters to the fourth. So part of me is thinking, man, we should have done this in millimeters. But remember, we're about to need this for something, and so maybe we'll get lucky, but I don't know. But notice we have all the ingredients we need now. Remember, the formula for what we're actually after here is sigma equals m times c divided by I. Now, let's do the top first. So again, I hate the fact that we're using C twice, but there's two different answers for this time. So let's do the compression. Let's do the top. So we were told the moment in this was 600 Newton meters. I wonder if we'll need to change that. 600 Newton meters times C. How far? Where's the maximum? If we're talking about compression on the top, where's the maximum compression? It is at the tip top of that, the highest point you can possibly get. That's that 0.05625 a minute ago. That's how far away that is from the neutral axis. 0.0, and that was in meters. So I'm wondering if we're glad about that. 0.05625 meters. So we got newtons and meters. And down on the bottom, we have this 0.0003453 meters to the fourth. Are we glad we did that in meters? We are, because the 2 meters on the top cancel with the 2 on the bottom, and now we have newtons per square meter. That's how we measured stress. Newtons per square meter is pascals. So this is the way it would be in the back of the book. Now, if you had it in millimeters down there, it's not wrong. You would just have some wonky unit, Newton square meter or millimeter to the fourth, and nobody would know what it meant. And of course, if you went to a table to look it up, will this material do it? That's not going to help, right? So it's going to be measured in pascals, just like our system is measured in PSI. It's got to be pounds per square inch or your table's not going to speak the language. So it actually was good that we had such a crazy number, but it's so tiny. The reason it's so tiny is meters are large. So this would have looked like a decent number if it had been in millimeters. And incidentally, what is mil is 1,000?
Yeah.
There's 4 of them, which means I'd have to multiply by 1,000 4 times, which would actually move its decimal point 12 places to the right. 12 thousands would move it 12 to the right. So that number would be like 34 million, in millimeters to the fourth, so to speak. So actually we kind of got lucky. This is going to come out correct. So compression up on the top, I stick that all in and I get 97 with 7376. 977,376, and that's newtons per square meter or pascals. Again, in the back of the book, you would see 977, would that be kilopascals or something like that? So we're in the same place we were before then, which is, oh, that top material up there, like, can it handle that? We got to go look that up someplace. Can it handle that many pascals of compression? And remember, it's not as simple as just who cares whether it's under compression or tension. I think you might agree this foam probably behaves similarly in tension or compression because it's sort of glued together with some, strange process, whereas concrete does not like tension, whereas it's fine in compression. Other materials like cables are great in tension, but they're terrible in compression. So the fact that we're actually calculating these separately, can have some relevance. So what about sigma for tension? In other words, the bottom, what's going to change? Well, not the 600 Newton meters. Well, the distance is going to change, right? That's the 0.11875 number because that bottom is a lot further away this time. So that's kind of fun. And then that number on the bottom is not going to change, right? So the only thing that actually changed is the distance. In this case, works out to be 206. 3348. Say it again. No, it's because the distance we just chose is that distance right there. It's literally just those teeny little fibers. So that's the weird part of this is notice there's just not much down there. But that's exactly why we converted it, not from just newtons to newtons per square meter, because it doesn't matter. Like we don't have to care what's down there. When you convert it to a force divided by an area, then you're just saying, what's the strength capacity of that material? So you don't have to go, oh, geez, I didn't realize there was hardly any wood down there. We would have had to do that if we said there was 900 newtons on it. And then we looked and went, whoa, you mean you're setting 900 newtons on top of this? But when you turn it to PSI, it's like, it doesn't matter. So interestingly, notice how different these two numbers are. One is 2 million pascals. The other is not even 1 million pascals. So it's like double. Why is it double? Because of the distance. That's entirely the reason. Notice the calculation is identical except for the distance. The distance is double. That's the reason. I changed this question to my own and just said I want the maximum tensile and compressive stress in the beam. Notice they said determine the resultant force the bending stress produces where? Just on the top board. Like they just said, who cares about the bottom? Let's just worry about what's on top. And that's okay as an engineer. Let's see. Yeah, I mean, did we calculate them? My gut reaction is we did it, right? Like that's the 977 number. So we just did both, I think is what it comes down to. And I just thought that was important because it's kind of neat to see that they're different.
I guess you find the force on the bottom part of the board. If it's the distance bottom.
That's right. And also you may notice they said determine the resultant force. They didn't actually say, they said determine the resultant force the bending stress produces on the bottom board. I'm sorry, on the top board. So since sigma, if you remember, was the force divided by the area, now that we know sigma and we know the area, we could turn that into force. So I think if we took that 977 number and stuck it in here, and then we divide it and we multiplied the area over there, then that would tell us how much force was actually on that board. So they were actually asking a different question. But I just thought it was kind of a confusing question for the fact that we're kind of just getting rolling in this. So the question I put, you know, on the test for this is going to be much more like this question here. Yeah, so what I'm thinking is, given that we're out of time, I'm thinking we do class kind of as per normal on Thursday, and I'll show you a little bit more about this, and then we have a little bit of time to review, and then just take it anytime you want on Friday. But I will warn you, just kind of in the interest of time, I'm sort of purposely trying to. Actually, let me show you this. I'll stop this recording and.